Okay, so let's dive into Unit 7, rotation, here in AP Physics 1. So we're going to start talking about rotational kinematics. So the good thing about rotation is that there's a lot of overlap between Unit 1, which is straight kinematics, to rotational kinematics, and there's a connection between the two. So the first thing in this video, we're going to talk about describing that motion. So again, the angular position, or like we referred to before, is just, it's of an object. It's the angle that it makes with respect to a given reference line. So if I'm here looking at my wheel, right, and I call this theta 0, okay, and my wheel rotates to a new position that we call theta, right? So we've changed the angular position, okay? Now, one thing for all the rotational motion that we're going to talk about in this unit, that counterclockwise rotation is always positive and clockwise rotation is always negative. And that, again, comes from the number line, or excuse me, the unit circle, where 0 degrees is here, 90, 180, 270, right? And so our positive angles go kind of up and to the left, right? It makes it in the counterclockwise motion. Now, when the object rotates, it's going to change its angular position. So as I go from theta 0 to theta, I now undergo an angular displacement. Just like when we talked about one-dimensional motion, when we change our position, we displace the object. So it's the same thing. When we change our angular position, we have an angular displacement. And so just like before, the equation, delta theta equals theta minus theta, one and right Q for that, theta 0. All right, and so that's the angular displacement equation. Now, once you start changing your displacement over time, you get an angular velocity, okay? Now, at any instant of time as you're rotating, you can have what is called a tangential, or excuse me, it moves tangential, right? And tangential means hitting the circle at one point, okay? And so this would be our linear speed, right? So how fast is it moving that linearly, as well as how fast is it rotating, okay? So just like with unit 1, I would have an omega, which is our symbol for angular velocity, would be delta theta over delta t, okay? But also, to bring in this translational, the translational or the linear velocity of the wheel would be simply the radius of the wheel times omega, right? And so the radius of the wheel will be from the center out, right? So if I multiply that times r, if I multiply that times omega, I get my v translational or tangential. Also, there is a relationship for for our angular position and that arc length, right? And so this is the linear distance that the wheel would move, okay? Now, as an object rotates, it's going to accelerate, right? To get it to go from 0 to a certain omega, we have to accelerate it. And again, it draws all these parallels back to linear, right? So alpha, which is our angular acceleration, is simply going to be delta omega over delta t, okay? Let me actually move that equation so it'll be easier to see later. Okay, so alpha is delta omega, so change in angular speed over the change in time. But also there is in addition to it accelerating rotationally, it also accelerates linearly. And so that alpha t, right, or AT, A translational or tangential, will be r times alpha. Okay, so just to kind of, and also there is a conversion factor, right? So the SI unit in all of this is going to be radians, right? So this is the SI unit. But sometimes the questions will talk about like, it'll talk about revolutions or angles, right? Or an angle. So one revolution, so one complete circle is 2 pi radians, which is 360 degrees, right? So if they give you like revolutions per minute or degrees per second, you need to convert to radians, right? So that's our SI unit. So you don't have to change your calculator, right? So we're going to treat radians as if it was like meters. So let's see how these equations work. Let me go in and let me highlight some of these things, right? So here's all of our important equations, right? These are what we call definitional equations. So these define those terms, right? These describe those terms, okay? And another important thing to note is that, I'll write down here, all objects, right, or all points on a circle will rotate with the same omega and the same alpha. Okay, I should have put that note in here. And one thing to note, like if I have something here versus something, if I have object 1 and object 2, they will rotate, their omegas will be the same, but their tangential speeds will not be the same. Okay, because remember that v tangential is r times omega. So even though they're going to rotate the same angular velocity, right, or angular speed, they're going to, because of where they're located, their tangential speed will not be the same. Okay, 2 will be greater than 1 because it's further away from the axis of rotation. All right, so let's look at an example problem. An airplane propeller rotates with an angular speed of 260 radians per second. Through what angle does the propeller rotate in 5 seconds? And if the propeller starts to rest, what angular acceleration does it experience? Okay, so we're going to use our definition of omega. So omega is delta theta over delta t. And we're going to solve this for theta, or delta theta. So this will be omega delta t. And so we don't have to do any conversion, right? It's in radians. So it's going to be 260, right, radians per second times 5 seconds. And that's going to give us an angular displacement of 1,300 radians. Okay. And so if you wanted to put that in degrees, right, 2 pi radians is 360 degrees. But again, in physics, our SI unit for angular motion will always be radians. Okay. Now, if it starts from rest, what angular acceleration does the propeller experience? So we say alpha equals delta omega over delta t. Don't have to do any solving here. It's solved for what we're looking for. So we say 260 minus 0 over 5, right? So it starts from rest, 0 degrees, goes to 260 radians per second. All right, and so all we're going to do is divide 260 by 5, and this is going to be 52 radians per second squared. Okay, so in this video, we focus on, we're looking at the descriptors. Next video, we're going to look at those kinematics equations that we did way back in Unit 1, but we're going to add an extra a to our cake term, so it's going to be like cake, right? Because we're going to look at constant angular acceleration, all right? And we're going to draw parallels between the two. And in this unit, we're going to draw a lot of parallels between linear and rotation,